Let's start the afternoon session. The chair of the afternoon session is Professor Grant Baba from Tokyo University of Science.
Thank you for introduction. Let's start the afternoon session. First speaker is Dr. Yuta Yamauchi from Yokohama National University. His title is the Total Absolute Curvature of Submanifold with Singularities. Please start.
Thank you for introduction. I am Yuta Yamauchi from Yokohama National University. So thank you very much for giving me opportunity to talk today. Today, I would like to talk about the total absolute curvature of submanifold with singularities. So today is two contents. So part one. So I will discuss the total absolute curvature of submanifold with singularities in general dimension and dimension. So I also present the generalization to Chan-Rush theorem to submanifold with singularities. So Chan-Rush theorem is a theorem about the total absolute curvature. But one-dimensional case. One-dimensional case. So part one will that ideal result. But part two. So if the curve is non-coorientable, in this case, so interesting results appear in non-coorientable case. So I will talk about the total curvature of non-coorientable curves. So first, I'll talk about the total absolute curvature of submanifold with singularities. Okay, so let me start by introducing the total absolute curvature for emergence. So let F be an emergence from an oriented closed manifold to Euclidean space, and B the unit normal boundary F, and G the Lipschitz-Killing curvature. Then the total absolute curvature, so tau, is defined. So this formula. So the total absolute curvature is the integral absolute value G over B. Yeah. So that total absolute curvature increases the degree of convexity or concavity and with the topological complexity. For example, on the top line, if the torus become bumpy, the total absolute curvature of torus increase. By the way, on the other hand, so if the genus of surface increase, the total absolute curvature also increase. So a famous result about the total absolute curvature is the Chan-Rush theorem. So F is an emergence from unrelated closed manifold and into Euclidean space. Then the total absolute curvature is greater than or equal to the sum of the bit numbers. Moreover, if tau is less than 3, so manifold M is homeomorphic to sphere. And if tau is 2, so 2 is the minimal possible value of the total absolute curvature. So tau is 2 if and only if the image of F is a convex hypersurface embedded in an n+1 dimensional affine subspace. So the Chan-Rush theorem is the result for the emergence without singularities, but the surface is singularities has already been studied. So Kozowski and Schaffner generated the Chan-Rush theorem to the surface is singularities in a three-dimensional Euclidean space. Then the total absolute curvature of surface is singularity defined by this formula. So the sum of Gaussian curvature and curvature function. So this kappa is the curvature function, the curve of image of singular set. So in this picture, this little curve is the image of a singular set. So the kappa is the curvature function of this curve. And so they proved this inequality. So right-hand side is right-hand side is equal to the sum of the batch numbers. So they generate the Chandler's theorem to surface is singularities. So but so this result concerns two-dimensional surface in three-dimensional Euclidean space. So I wonder whether it is possible to the general dimension and codimension. And so Kosowski and Schaffner's theorem does not imply the relation between minimality of the total absolute curvature and convexity. So okay, so I expect some relationship between minimality and convexity. So in the case of singularity. So, okay. So today I would like to introduce two theorems, theorem A and theorem B. So theorem A, so let F be a co-oriental admessive frontal. So I'll introduce the notion of admessive frontal later. So then the total absolute curvature of admessive frontal is greater than or equal to the sum of the batch numbers. Moreover, if tau is less than 3, so manifold is homomorphic to a sphere. And if tau is 2, then the image of F belongs to an n+1 dimensional affine subspace. So the difference between Chandler's theorem, so tau is 2 does not imply the convexity of the image of F. So but if I add condition on singularities, there is a relationship, minimality, and convexities. So if a singular set is not empty and consists of singular point of the first kind, then so tau is 2 if and only if these three conditions holds. So then so the image of F is a closed convex domain of an n-dimensional affine subspace. So this is a relationship, minimality and convexity with singularities. Okay, so I'll talk about the frontal as singularities. So let a map for map F. So if P is regular point, if one no leaf, so the rank of derivation of F is equal to N. So otherwise, we call P a singular point. So in this talk, we assume that the regular set of map F is dense in M. So then, so we call F is frontal. If every point P, there is an open neighborhood to U, and there is a map from U to oriented Grassmannian, such that the derivation of F belongs to pi. So, okay. So this map pi represent a moving plane tangent to F. So this time we call F frontal, and pi is called the general gas map of F. So a frontal has a property that immersion don't have. So this is co-orientability. If if the generalized gas map pi can be defined globally on M, so the general gas map is well defined on M, then we call F is co-orientable. So so in this figure, there are two one-dimensional frontals. The arrow indicates a tangent line and its orientation. So in the right figure, at this point, So the general gas map is not well defined. So the right one-dimensional frontal is not co-orientable. But if so, F is non-co-orientable, taking its dark cover makes F co-orientable. So without loss of generality, so we may assume that F is co-orientable. So in this talk, we focus the co-orientable frontals. So next, let me explain singular points for detail. So let F be a frontal. Then we define a function lambda by this formula. So lambda is a determinant of the matrix partial derivative and moving frame of orthonormal space of generalized gas map pi. So then, if lambda p is 0 if and only if, so p is a singular point. So, okay. And this property is independent of the choice of coordinates. And we define the non-degenerate. A singular, if so, the derivative of lambda does not vanish at p, then we call a singular point p is non-degenerate. So non-degenerate singular points are classified into the first kind and the second kind. So let sigma f be the set of singular points on N. So if all singular points are non-degenerate, then the singular set sigma is a regular hypersurface on N. And if P is a non-degenerate, then the kernel of derivative of F is a one-dimensional linear subspace. So using this kernel, we classify non-degenerate singular point into two types. So P, if the kernel is not contain the tangent space of sigma, then we call P is a singular point of the first kind. Otherwise, we call P a second kind. So, and this is a very important property of the singular point. So if every singular points are all of the first kind, then the image of the singular set is a regular submanifold in Euclidean space. So as F, so restriction to the singular point is an immersion. When so all singular points are of the first kind. Yeah. And so we would like to define the atomistic frontals. Let CF be the set of the singular point of the second kind. Then a frontal is called admissible frontal. First, if all singular points are non-degenerate and there is the hypersurface such as CF is contained in H. So then we call F an admissible frontal. So there are many examples of admissible frontals. So for example, frontals having at most AK type singular point. So this singular point is very genetic singular point. So in this case, frontals are admissible. In addition, frontals whose singular points are only the first kind is also admissible. Because so in this case, so CF, the set of a singular point of the second kind is empty set. So this frontal is also admissible. So in this picture, some example of the admissible frontals. So okay, on the left, so this frontals and the set of the singular point of the second kind is empty set. So this edge-like part is the image of a singular point. So on the right, so in this case, the CF is discrete subset. So this point is the singular point of the second kind. So this frontal is also admissible frontal. Okay, so next let us look at the single set. So F is defined by this formula. So then the single set of F is a surface in the three-dimensional Euclidean space. So in this picture, this yellow surface is a single set, and the F, the set of the singular point of the scanner kind, is a regular curve. So this blue curve is the set of the CF. So in this case, CF is a regular curve on the surface C1F. So this element F is also admissible. So next, I will explain the total absolute curvature. So for the general gas map of pi of F, so we will define the bundle B. So B is bundle such that this the unit vectors orthogonal to the general gas map pi. So B is called the unit normal bundle of F, and we define the Lipinski curvature on B. So for a point of B, P xi, and in this case, so P is a regular point. Then the Lipinski curvature G is defined by the determinant of the shape operator with respect to the unit normal vector G. So this is a definition of the Lipinski curvature. So Lipinski curvature is determinant of the shape operator. So the Lipinski curvature is a generalization of the Gaussian curvature in general dimension and codimensions. So Lipinski curvature can be defined only on regular points. So this curvature can't be defined on the single set. But we have the method that's a generalization Lipinski curvature over a single set. So we call this map nu, the canonical gas map. Then the pullback, the volume element of unit sphere. So the pullback of the volume element of unit sphere by nu is equal to this n plus r minus 1 whole. So so this pullback can be written by using the Lipinski curvature. So the left hand side can be defined on over to the entire B. So G can be defined only on regular set, but so this form can be generalized continuously over a single set, the entire B. So we also same proposition. The absolute value G and d mu B is a continuous, so n plus r minus 1 form on B. Okay. So we can integrate the absolute value of G over B. So but before defining total absolute curvature, I have to introduce this F bar. So let F be an admissible frontal. Then, F bar is the reflection of F to singular set. Then, this F bar is also a frontal. So there the new frontal F bar exists in the admissible frontal. So okay. So let B bar is the unit normal bundle of F bar, and G bar, the Lipinski curvature of F bar respectively. So okay, so we define the total absolute curvature for admissible frontal using this. So for our co-oriented admissible frontal F, you define the total absolute curvature as this formula. So the total absolute curvature tau is the sum of total absolute curvature over regular set and total absolute curvature over a singular set. So this sum is the total absolute curvature for atomistic frontal. So if we consider only the total absolute curvature of the regular set, it has non-trivial lower bound. So this term has non-trivial lower bound. So for example, for position number F, for position number A, the FA is defined by us, right? Then the total absolute curvature of the regular set satisfies this inequality. So for positive number epsilon, so we can take A such that this such that satisfies this inequality. Then the total absolute curvature of the regular set is less than for positive number epsilon. So it has non-trivial lower bound. So okay, so we have to so we need not only total absolute curvature of the regular set, but also the total absolute curvature of singular set. Okay, so let's introduce the theorem L. So let F be a co-orientable atomistic frontal from oriental closed manifold into Euclidean space. Then the total absolute curvature is also greater than or equal to the sum of the Bethe numbers. Moreover, so if tau is less than 3, so M is a homeomorphic to a sphere. And if tau is 2, and the image of F belongs to a plus 1 dimensional affine subspace. So in this case, tau does not imply the convexity, but sorry. Okay, so okay. So I introduce the outline of the proof of theorem L. For unit vector U, the height function HU is defined by the inner product F and U. Then, so for atomistic frontals, the subset Q, Q is a set. Q is a set of unit vectors such that the height function is not a Morse function. So this subset Q has measure 0, and for atomistic frontal, so the total absolute curvature tau is equal to the average number of critical numbers of height function. So in this formula, so the total absolute curvature can be written by using the number of critical points. So by the most inequality, so almost every unit vector U, then the number of critical point of height function is greater than or equal to the sum of the Bethe numbers. So integration, so both sides. So the left-hand side does not change, but so sorry, right-hand side does not change, but left-hand side is equal to the total absolute curvature tau. So we obtain so tau is greater than or equal to the sum of the Bethe numbers. Okay, in addition, so if we show the proof of tau, if tau is less than 3, so M is a homeomorphic to sphere. So if tau is less than 3, then so this subset such that so critical the number of critical point is exactly 2 is not empty, because so if this set is empty, so the total curvature is greater than or equal to 3. So this is a contradiction. So this set is not empty. So there is a height function such that having critical point, having 2 critical points. So by this theorem, so M is homeomorphic to any dimensional sphere. And next I show the proof of, so if tau is 2, the image of F belongs to n plus 1 plane. So if the image of F does not belong to every affine subspace in Euclidean space, then we can show that the tau is greater than 2 whole, so which is a contradiction. So F belongs to an n plus r minus 1 affine subspace. So by repeating the process inductively, so we can show that F belongs to an n plus 1 affine subspace. Good. So the theorem A does not imply the relationship between minimality and convexity, but so if we add a condition, singularity, we can see that relationship between minimality and convexity. So suppose that the single set is not empty and consists of single points of the first kind. So all singular points are of the first kind. Then tau is 2 if and only if these three conditions hold. So first, the manifold and the single set are homeotic sphere respectively. Second, the image of F is a closed convex domain of an n-dimensional sphere affine subspace. And the single set image coincides with the boundary of the image of F. So in this case, so this n is very unique result. So F is a map from any manifold, but so image of F is contained to any dimensions affine subspace. This is a very unique result in the case of singularity. Okay, so we introduce I will introduce the outline of the proof theorem B. So if all singular points are the first kind, then so F bar, so this is the restriction of F to single set. So this is an immersion. So for immersion, the total absolute curvature is greater than or equal to 2. So in this case, tau is 2. So if and only if the total absolute curvature on the regular set is 0, and the total absolute curvature over the singular set is just 2. So by using the Chern-Rashoff theorem, so image of singular point is a convex hypersurface in an n-dimensional plane P. In addition, so this is a regular set. So the image of regular set coincides with the interior of the image of the singular set. So in this picture, so this blue part is the singular set. So singular set is a convex hypersurface is an n plane, and so remaining part, so singular set is a singular set, so contained in the n-dimensional plane P. So first, the image of F is a closed convex domain, and so the image of singular set is the image of a singular set coincide with the boundary of the image of F. Okay, so I'll show you example. So so consider the orthogonal projection from a sphere, from a unit sphere. So F is defined by a slide. then the singular set sigma f is so L minus 1 unit sphere. And so all singular points are all the singular points are the first kind. So, so this frontal f satisfies assumption of theorem B. So then, so the total absolute curvature of this map f is 2. And so, first, so image of f is a closed convex domain, and the image of f, image of singular set is the boundary of image A. So this is an example of theorem B. Okay, so I will introduce the two-dimensional case. So in the case of n is 2, so f is an admission frontal if and only if all singular points are non-degenerate, and the set CA, the set of the singular point of the second kind, is a discrete subset of sigma. In addition, if codimension is 1, the total absolute curvature is written as this formula. So the sum of integral Gaussian curvature and curvature function. So this part and so this curvature function. Okay, so this is a theorem proved by Kosowski and Schaffner. So they suppose that f be a co-oriented admissible wavefront. So wavefront is frontal is a regular Legendre rift. And suppose that this condition. So f is an admissible wavefront. Then they show that this inequality. So the total absolute curvature is greater than or equal to the sum of the Betch numbers. And so applying theorem A and B to do two-dimensional case, so we obtain corollary C. So I suppose that f be an co-orientable admission frontal. Then first tau satisfies this inequality. Moreover, if singular points are of the first kind, then are of the first kind and tau is 2, then the image of f is a closed convex domain over two-dimensional affine subspace of three-dimensional Euclidean space. Furthermore, Kosowski and Schaffner suppose that wavefront. There are some examples such that there's some frontal with total absolute curvature is just 2, but not wavefront. So it is necessary. It is necessary to generalize the setting from wavefront to frontal. Okay, so finally, let's discuss a one-dimensional case. So for co-oriental closed one-dimensional frontal, then the total absolute curvature tau is can be written as this formula. So the sum of the curvature function and the number of singular points, and so tau is greater than or equal to 2. Moreover, if singular point is not empty, so tau is 2 if one no leaf, gamma is a line segment. But if singular set is empty set, so gamma is if gamma is a regular curve, then the integral of curvature function is greater than or equal to 2 pi. So this is a Fenhel's theorem. On the other hand, so if singular set is not empty, then by co-orientability, so that number of singular point is uneven number. So in this case, so sharp sigma f is greater than or equal to 2. So So this satisfies this inequality very easily. So this inequality is very trivial for co-orientable case. So there is a question, what about the case when gamma is non-co-orientable frontal? So, okay, so next, so I talk about the total curvature of non-co-oriented one-dimensional frontals. Okay. So first, so I'll introduce the theorem, this theorem E. This is a Fenfield type theorem for frontals. So the total curvature of a closed non-co-oriented frontal is greater than or equal to pi, and it is equal to pi if and only if the following three conditions hold. So first planar, next convexity, and the condition 3 is a rotation index. So this figure is a closed frontal with the minimal total curvature. So from now on, we consider one-dimensional case. So the domain, so manifold M is into circle, and gamma is a closed frontal if and only if. So this gamma is a 2 pi periodic frontal. And by definition of frontal, there exists a unit tangent vector field E, such that so derivative of gamma and the unit vector field E is linearly dependent. And so in this time, so closed frontal is co-orientable if and only if there exists a 2 pi periodic unit vector field E. Otherwise, so if there exists a unit vector field such that so t plus 2 pi is equal to minus et, then this closed frontal is non-co-orientable. So in this part, we focus non-co-orientable frontals. And so, okay, so we can define a curvature function like a regular curve. So for a frontal gamma, the curvature kappa defined by this formula, but this kappa defined on the regular set. So the kappa can be defined on the singular set. So this product, cap and the norm of derivative of gamma is equal to the norm of the derivative of unit tangent vector field E. So this one form, kappa ds, is a continuous one form on a domain, entire domain. So we can integrate this formula. So for a closed frontal gamma, so that total curvature for curve of gamma is defined by this formula. So we call T the total curvature for curves. So note that so tau is can be written by using this tau. So tau is equal to T plus the number of singular points. So but in the case in this non-co-orientable case, T is more important than this tau. So in this part, we focus on this total curvature for curve T. Okay. Okay. So in this slide, I show the proof of the total curvature for curve is greater than or equal to pi. So then the unit vector field E is a curve on unit sphere. So in this time, so let L be the length of the unit tangent vector field E. Then this L coincides with the total curvature T. So L is equal to T gamma. So it is sufficient to show that L is equal to L is greater than or equal to pi. So if gamma is non-co-orientable, then the curve E has a common point with every great circle of a unit sphere. So this is very important property. So because by using this further summation lemma, we can show this inequality. So this further summation states that let L be the length of a closed curve C on unit sphere. So this time, if for every great sphere G, so G intersect every great hypersphere G intersect the curve C, then L is greater than 2 pi, or L is 2 pi and C is consist of 2 half arcs of great circle. So by using this lemma, we can easily show that L is greater than or equal to pi, and if the gamma is pi, this time the image of unit vector field E is half arcs. So gamma is planar frontals. So for a non-coorientable closed frontal gamma in plane, so when does the total curvature is equal to pi fold? So for this question, the rotation index and L convexity are keys. So first, I'll introduce the rotation index. So for a non-coordinate closed frontal gamma, we set an angle function sigma as the angle of unit tangent vector field E. So this time, gamma is non-coorientable. So E2 pi is equal to minus E0. So the angle theta 2 pi minus theta 0 is odd number multiple of pi. So there exists a number integer such that this formula. So that we defined this m plus 1/2. So the rotation index gamma is defined by this formula. So m plus 1/2. Okay, and next, I introduce the L convexity. So the frontal F is L convex. If a function L does not change its sign, and L is defined by this formula. So L is determinant matrix E and derivative of E. So in this time, curvature is curvature. So the signed curvature function. So in this time, L is equal to a product curvature and the norm of derivative of gamma. So if L is convex, gamma is convex, if and only if this curvature, the signed curvature function, does not change its sign. For example, on the left, this frontal is L convex, but on the right, this point, L changes sign. So this frontal is not L convex. So L convex is convexity for curves with singularities. Okay, so now I introduce theorem E. So total of curvature of a closed non-coorientable frontal is greater than or equal to pi. And it is equal to pi if and if. So the following three holds. So first, curve is planar frontal, and curve is L convex. So have L convexity. So third, the curve's rotation index equal to plus minus 1/2. So this frontals is so the total curvature for curves is equal to pi. So by the way, Penhal's theorem states that for a closed regular curve gamma, the total curvature is 2 pi whole, and it is equal to pi if and only if gamma is an over. So over is a simple closed convex curve. However, in the case of non-coordinate frontal, so in the case of singularities, their non-simple closed frontal is the minimal total curvature. So in this case, this frontal having these frontals have the minimal total curvature for curves. So there is a question: when does the closed non-coordinate frontal gamma is t is equal to pi become a simple closed curves? So one of the answer for this question is theorem F. So let gamma be non-coordinate frontal and suppose that so t is pi, and every single point is a cusp. So in this time, so let n gamma be the number of cusps, so number of singular point. So then first, this number of cusps is an odd integer satisfying n is greater than or equal to 3. And so this is a condition about simple. So the number of cusps is just 3 if and only if so gamma is a simple closed curve. So there are no simple closed non-coordinate frontal such that having for 5 cusps and or 7 cusps. So simple closed curves have exactly 3 cusps. So this figure is the closed frontal is and gamma is equal to 3 and the total curvature is equal to pi. Also, okay. So I explain the cusp. The cusp is a singular point, so such as there exists a coordinate change psi, there exists a local deformism of two-dimensional Euclidean space, so large psi, such as satisfying these formulas. So this curve is great. So this point, so this singular point is cusps. So suppose that all singular points of a closed frontal gamma are cusps. Then gamma is non-coorientable if and only if the number of cusps is an odd number. So okay. Okay, so lemma A, so let gamma be a frontal, suppose that's a start point, and a start point coincides with end point. And gamma is the restriction from 0 to 1 open section is a regular curve. Then the total curvature of this curve is greater than pi fourth. So so we can show that the number of cusps is greater than 3 by using this lemma A. Because so first, if all singular point cusps by non-coorientability, the number of cusps is an odd number, satisfying so n gamma is greater than or equal to 1. But if n equal to 1, then so lemma A states that so t is greater than pi. So this is a contradiction. Our assumption is the total curvature is equal to pi. So therefore, n is odd number satisfying greater than or equal to 3. So okay, so next, so I showed that if so gamma is simple closed curve if and only if the number of cusps is 3. Okay, so I showed that gamma is simple imply the number of cusps is 3. This is easy than converse of this. So denoted by omega, so the region bounded by gamma, so this area. So in this time, so by using the Gauss-Bonnet theorem, so the number of cusps of partial omega is equal to 3. So, the boundary of omega is a closed curve gamma. So the number of cusp is equal to 3. Okay. So next, I'll introduce the converse. So if n is 3, then gamma is a simple closed curve. So it is suffice to show if the number of cusp is equal to 3 and gamma is not simple, implies the total curvature is greater than pi. So suppose that gamma has 3 cusps and there is a point, the self-intersection point. Okay. So in this term, we can classify self-intersection into 3 cases. So first case 1, case 2, and case 3. Okay. So in the case of 1, this curve contains a closed curve such that start point coincide with end point. So the total curvature of this blue closed curve is greater than pi. So by lemma A in this case, in the case of 1, total curvature is greater than pi. So this is a contradiction. So next, we investigate the total curvature of the following 2 closed curves. So 1 cusp and 2 cusp. So 1 cusps correspond. Okay, so this part. And 2 cusps correspond to this part. Okay, so first, for about 2 cusps, so lemma B. Suppose that start point coincide with end point, and gamma has cusp, 2 cusps. So in this term, and let phi be the angle of at the end point. So in this term, the total curvature for this closed curves is greater than or equal to pi minus phi. Also, lemma C, this is 1 cusp. So in this case, the total curvature of these curves greater than pi poles. So by using lemma B or lemma C, C, we can show that these curves have total curvature is greater than pi. So the curves satisfies assumption of lemma C is divided by 16 cases. So in the paper, we check 16 cases that curves that total curvature of curves is greater than pi. Okay. So by lemma C, the total curvature of this curve. So this part is greater than or pi, and this part is greater than or pi minus phi. So the total curvature of entire curve is greater than pi whole in the case of 2. So this is a contradiction. And by lemma B and lemma C, so this part is greater than pi, and this part is greater than or equal to pi minus phi. So the total curvature for entire curves is greater than pi fourth in the case of 3. So by the contradiction, we have complete proofs. So the number of cusps is 3 if and if gamma is simple closed curves. Okay. Okay, let me conclude with summary. So part 1, we discussed the admissible frontals, and we define the define the total absolute curvature for all-dimensional frontals. In this time, so the total absolute curvature tau is greater than or equal to the sum of the bit numbers, and if tau is 2, then the image of F belongs to the n plus 1 plane. And theorem B, so singular points are all of the first kind. In this time, tau is 2 if and only if first, so M is homeomorphic to n-dimensional sphere, and the singular set is homeomorphic to sphere. And the image of singular set coincides with the boundary of the image of F. And finally, the image of F is a closed convex domain in n-dimensional plane. So part 2, so we discuss the non-cooriental one-dimensional frontal. So theorem E, so for closed non-cooriental frontal, then so total curvature is greater than or equal to pi, and T is equal to pi if and if gamma is planar, L convex, and the rotation index is plus minus 1/2. And theorem F is the theorem about simple closed curves. If the total curvature is equal to pi and all the singular points are cusps, first the number of cusps n gamma is an odd number such finds is greater than or equal to 3. And so if t is equal to pi, the number of cusps is exactly 3 if and only if the gamma is simple closed curves. Okay. This concludes my talk. Thank you for listening.
Thank you very much. Then any question or comments? So, there any future direction on these topics?
Yes. So yeah, okay. Part 2. So I discussed one non-commutative one-dimensional frontal. So but I'm interested in the non-commutative, so generally n-dimensional frontal. So such frontal. So the total curvature, also the curvature of non-commutative frontal have so non-trivial lower bound. So this is my interesting topic.
Any other question or comments? Okay. Let's thank speaker again.